Hey folks, so welcome back to another lesson, and today we're going to look at satellites and curved reflectors. Now, unfortunately, there is a bit of practical work with this, especially the curved reflectors, which we can't do. But when we get back into class, we will have a look at some of these because it's a nice wee bit of practical. So hopefully you remember about the definition of satellites. This is an object that orbits around another object in space. So it could be the Earth around the Sun or the Moon around the Earth. Now in this case, when we talk about satellites, we're really talking about man-made objects which basically orbit around the Earth. So what I'd like to do first of all, folks, is to copy this wee bit down. So you know that we're talking about satellites that are orbiting around the Earth at different heights. And this one here, I really want to put a wee box around it once you've written it down. And this is the time for one complete orbit is called the period. So this is the time it takes a satellite to go around the Earth once is called the period. It's a bit like how you have a period in school, which is the time it takes for one lesson to happen for a subject. Now, the higher the orbit, the longer the period. And that kind of makes sense because if you think about it, the higher up it is, then the bigger the circle that satellite has to trace or travel through, so the longer it takes to go around that planet. So again, that's worth noting down as well. Now, there's a really special satellite called a geostationary satellite. And this is a satellite that has a period of 24 hours. So what that means is it takes 24 hours for the satellite to go around planet Earth. In order for the satellite to be geostationary, it must have a height of 36,000 kilometers. So there's two ways to describe a geostationary satellite. One is that it has a period of 24 hours, or two, it is at a height of 36,000 kilometers. So it goes around the Earth like this. Now, why a geostationary satellite is important? Well, first of all, it's got a period of 24 hours. So that means the satellite follows the same part of the Earth all the time. So say, for example, we have a satellite that is above the school and it's geostationary, then it would always stay above the school regardless of what time of day it is. And this would make it an ideal spy satellite to spy on lazy pupils. So what are the benefits of satellites? Why do we put all these things up into space? Well, first of all, if you've ever used GPS, if you've ever used Google Maps, or if you ever used a GPS system in your car, you've used a satellite because the satellite uses the information it sees from up above in the sky to plot where you are and where you want to go. If you've got Sky television at home, you've probably used satellite communication, especially if you're living up in the hills where you don't really get very good reception. Satellite reception is the only way you can really get TV or internet in some cases. Weather forecasting, if you've ever looked at the weather to see whether it's going to be freezing, raining or sunny, that relies on weather satellites to predict where the clouds and the sunshine is going to be. And last but not least, scientific discovery and space exploration. A lot of those photographs that you put into your PowerPoint about the definitions of stellar objects, some of them probably came from a telescope. Some of them might even have come from the Hubble telescope, which is actually a satellite of the Earth. Okay, now we're kind of switching pace a little bit because we're looking a little bit more about how we use satellites. So one of the things you might have done in second year and first year is the law of reflection. And I'm going to do a wee video which I'm going to put on YouTube so you can play around with this. Unfortunately, I can't let you do it practically because we're not in class, but when we go back to class, we will look at doing this as an experiment. So the idea of this experiment is very simple. Is that you have a mirror, which we call the interface. You have a ray box, which gives out a single light ray. And you have this thing that we draw in, which we call a normal. And I'll explain what more of that is in the video. So please watch that video to get a bit more physics other than just this lesson here. And we have something called the angle of incidence and the angle of reflection. And the key thing here is that the law of reflection states the angle of incidence is equal to the angle of reflection. So what that means is the angle this light hits the mirror, so this angle here, it's called the angle of incidence, will be the same as the angle the light bounces off, called the angle of reflection. Now, this doesn't just apply to light waves, it can apply to things like sound waves, it can apply to things like water waves, it can even apply to things such as like a football or a tennis ball, or even a snooker ball. If you've ever played tennis or football or even basketball, you know if you hit the ball off at an angle, it will usually bounce off at the same angle. And that's how sportsmen know how to get their angles correct. It's because of this law of reflection. So this law is really, really important. And as I say, try the demo on PhET Physics. This is the website I'll put on for you to try it yourself. Now, why do we need to know about the law of reflection? Well, we actually use this in a very important way. So before we get to it, let's have a look at this problem here. Why do satellite dishes all have this shape? If you don't believe me, look out in your street and I guarantee you will probably see lots of people who have satellite TV will have one of these dishes outside their house. So this is a very special shape and it is called a parabolic receiver. So I would like you to try and remember this term. You can write this down in your notes, and any satellite dish is really a parabolic receiver. Now the key thing we want to know is why do we have the receiver located here? And again, if you don't believe me, look out in the street and I guarantee you will see all of the satellite dishes with a satellite receiver at this position or somewhere near it. Why is it not over here? Why do we even have it at the front? So we're going to use some physics to explain that in the next couple of slides. So again, you would do this experiment in class, and what we would do is we would have a curved mirror and we would shine 3 light rays into it as it is on the diagram. And this is called a ray diagram because notice we've got the light rays coming in, and when you draw these, I want to use a ruler and I want to draw an arrow showing which way the light's going. Light rays always travel as straight lines. This is why we use a ruler, and the arrow tells us where it's coming from and where it's going to. So here we know the light rays are going into the mirror and then they would bounce off like this. So the light rays, as I said from previously, they come in here and then they bounce off or reflect off here. Now this one also is a light ray, but it just bounces back the way it came. And notice how all the light rays seem to meet at one single point in the middle here. And that's a really special point which we call the focal point. So all waves reflected by the dish will meet at this point. So what I want to do, folks, is to copy this diagram. Remember, use a ruler and copy this wee bit and this bit as well. At the focal point, waves can combine and provide a stronger signal. So you can now understand why we put the detector here, because if we put it here, that means all the sound waves will collect here, and that means it makes them a lot stronger. Because the thing you have to remember is that those satellite signals are coming from 36,000 kilometers above you. So they're traveling very big distances. They probably get very weak by the time they reach you. So the more of these we can collect and combine together, the better your reception is going to be. Now, we use these parabolic reflectors in real life. You've probably seen them one outside your street. But we also use them for astronomy. And you might remember this telescope that I mentioned to you called the Arecibo, which is now no longer working, unfortunately. But you can see here, this is actually a big parabolic dish, and you have the receptor over here. And the idea is you can move this along by these pulleys here, so you can change which part of the sky this telescope is looking at. And so this is a real application of parabolic reflectors. Now, another use of it, which you might not be aware of, is in cars or in torches. So why do headlights or torches have a curved reflector behind the bulb? Again, if you don't believe me, have a look at a torch or have a look at a car, you will probably see this parabolic dish just sitting behind the bulb. So why is it that we have that? Well, first of all, if we look at the curved transmitter, remember this is where the bulb is, and if we draw the ray diagram showing where the light goes, some of the light will actually go back the way and they will hit the curved reflector. Now, in this case, instead of the waves collecting at the focal point, they will actually spread out as if you were kind of going the other way. So what the curved reflector does is it actually makes your light rays go out in straight parallel lines. In other words, you get a nice beam effect. And so this is why you have curved reflectors on the back of your bulb in a torch and in a car headlight. It's because it makes it into a nice beam. So waves emitted, which means it's given out from the focal point, will be reflected by curved transmitter and parallel beams. And the curved reflector can work as a transmitter or as a receiver. Excuse me. So I would like you to make a note of this diagram and also of the notes down at the bottom. And hopefully you can now explain why we have parabolic receivers on satellites, torches and car headlights.